All right, let's talk Java. If you're getting ready for a tech interview or you're just trying to squeeze every last drop of performance out of your code, you are in the exact right place. Today, we're diving into one of the most powerful concurrency tools in the JVM, the fork/join framework and its super convenient sidekick, parallel streams.
So, let's kick things off with a simple question. You've got this awesome multi-core processor sitting in your machine, right? But is your code actually using all of them? Most of the time, a standard application just runs on one core, leaving all that other horsepower completely unused. It's kind of like having an 8-lane superhighway but forcing all the cars into a single lane. This is the exact problem that the fork-join framework was built to fix.
And that, right there, is what we call the multi-core CPU problem. We have all this amazing potential just sitting there in our hardware. So the real challenge is, how do we smartly break up our work and spread it across all those cores to get things done way, way faster?
And that leads us to Java's really elegant solution. The fork/join framework is all about that classic divide and conquer strategy, but it's been totally supercharged for the hardware we have today.
Okay, here's the definition you're going to want to remember for any interview. It's a specialized framework, and that word is key. It came out way back in Java 7, and it's specifically for tasks you can break down over and over again. And the most crucial part, it's optimized for CPU-intensive work. We're talking heavy-duty calculations, not sitting around waiting for a database to respond. The strategy is actually really simple when you look at it. It's just 3 steps. First, you take a big, complex task and you split it into smaller, bite-sized pieces. Next, you execute all those little pieces at the same time, in parallel, on different CPU cores. And finally, you take all those individual answers and combine them back together to get your one final result. Simple, right?
So let's get into the nitty-gritty of how the code actually works. Imagine you're splitting a job in 2. When your code says left.fork, the thread you're on is basically saying, hey, some other worker thread, go start on the left half. I'm not going to wait for you. That happens asynchronously. Then your original thread immediately gets to work on the right half by calling write.compute. That's synchronous. It does the work itself. Once it's done, it calls left.join, which is its way of saying, okay, I'm finished. Now I'll just wait here until that other thread is done with the left half, and then we can put our results together. That whole fork, compute, join dance is the absolute heart of how this thing works.
Now, this all sounds pretty cool, but what makes the fork/join framework so much more efficient than, say, a regular thread pool? Well, the answer is its secret sauce, a really clever algorithm called work stealing. And trust me, this is a huge interview topic.
So how does this work stealing thing actually work? Well, picture each worker thread with its own personal to-do list. Technically, it's a DQ, which just means it can pull tasks from the front or the back. A thread normally just chugs along, working on tasks from its own list. But here's the magic. If a thread finishes all its work and has nothing to do, it doesn't just go on a coffee break. Nope. An idle thread will actually go look at another thread's to-do list and steal a task to work on. This is brilliant because it keeps all the CPU cores busy all the time. It's a self-balancing system.
And hey, if you really want to nail it in an interview, here's your golden one-liner. Just say this: work stealing is all about maximizing CPU utilization by dynamically moving work to where there's free capacity. It's just an incredibly efficient way to handle load balancing.
Okay, so fork/join is clearly powerful, but let's be honest, writing those special task classes can feel a little clunky. So now let's talk about the much more common way you'll use this power, parallel streams. Think of this as the easy-to-use shortcut.
So what is a parallel stream? It's really just a regular Java stream that's been told to run its operations in parallel. But the key thing to get is that under the hood, it's using the exact same fork/join framework we just talked about. You don't have to manage any threads yourself. You just call .parallelstream, and Java handles all that complexity for you.
So the choice between a regular stream and a parallel stream really comes down to a trade-off. A sequential stream is simple, it's predictable, and there's almost no overhead. A parallel stream, on the other hand, can give you a massive performance boost, but it comes at the cost of higher coordination overhead. You're basically trading some control for a whole lot of convenience.
Okay, listen up, because this is probably the single most critical thing to understand about parallel streams. By default, all parallel streams in your entire application share one single JVM-wide thread pool. It's called the common pool. This isn't your own private pool for your task. It's global. And this has huge, huge implications, as we're about to see.
Right. Because of that shared pool, knowing when not to use these tools is maybe even more important than knowing when to use them. So let's get into the critical traps and best practices that are going to keep your apps running fast and, more importantly, stable. So here's the bottom line. You have to use fork/join and parallel streams for the right kind of job. This table breaks it down perfectly. You want CPU-bound tasks, not I/O-bound tasks that wait for things. Your operations need to be independent, not blocking. And your code should be stateless, not messing with shared mutable data. If you block a thread in that shared common pool, you could literally starve other critical parts of your application. So the rule is simple. Fork/join is for number crunching, not for waiting.
Let's be super explicit here. Just don't do it. Do not use parallel streams for tasks that involve I/O, like hitting a database or calling a REST API. Don't use them on tiny datasets either, because the overhead of splitting everything up will actually make it slower. And definitely avoid them if your code is stateful or relies on shared mutable data.
And this right here, this is a perfect example of what not to do. You've got multiple threads all trying to call add on the same non-thread safe array list at the exact same time. This is a textbook race condition. It's a complete disaster waiting to happen. You're going to get wrong answers, weird exceptions, and a really bad headache. It's a massive anti-pattern.
So if you can't use fork/join for I/O, what should you use? That's where our old friend the executor service comes in. It's designed for exactly that, independent tasks that might block. Fork/join is for your recursive, CPU-heavy work. The executor service is your go-to general-purpose tool for pretty much everything else, especially I/O. It's all about using the right tool for the job.
Okay, to bring it all home, let's just hammer through these common interview traps. Ready? No, going parallel is not always faster. No, parallel streams won't always make your code better. Absolutely not. It is not safe to do I/O in parallel streams. And for the last time, no, they do not get their own thread pool. They all use that one shared common pool. If you can avoid these mistakes, you're already ahead of the game. And we'll end with this. This is your perfect polished summary for any interview or technical chat. It shows you understand the power of the framework, you get the efficiency of work stealing, you appreciate the convenience of parallel streams, but most importantly, you know about the critical danger of blocking that shared pool. So, next time you're writing code, just ask yourself, is this really a job for